Hi everyone. In this video I'll be going over 11.3 and 11.4. We're skipping 11.2. We're going right into ellipses. So we're going to start this video by graphing what's called an ellipse. You can kind of think of it like an oval. Sometimes we use that terminology, more widely in just common parlance. This is what an ellipse can look like. This right here is an ellipse centered, quote unquote, at 0, 0. So that value a, not a squared, but the value that's being squared is how far we count this way and then make our vertex. This number b is how far we count vertically. B is always associated with the y, so you can kind of think of like whatever number is under the y term is your vertical information. Whatever number is under the x term is your horizontal information, right? X horizontal, y vertical. It should always be equal to 1, right, if it's in standard form. So let's see how we might use this to graph an ellipse. So I'm going to go down to example 1. So with this one, we have x squared up top, and then I have 25 below the x squared. So that would be like 5 squared, just to get it in terms of something squared. Something squared. And then plus y squared over 3 squared, right? That's acting like b. So for example, a is 5 and b is 3 in terms of this information here, right? So from the center, I'm going to count 5 to the right and left, and then I'm going to count 3 up and down. So here's the center. And that's because we haven't shifted anything, right? It's not x minus and then squared. It's not y minus or plus a number and then all squared. It's just zeros. So that's why I'm centering it at 0. So from there, from the center, I'm looking at this number right here, and I'll count 5. And then I'll go to the left. 1, 2, 3, 4, 5. From the center, I'm now going to count 3 up. Just draw your best kind of football-shaped ellipse that you can. It's kind of difficult to draw these things, but just make sure your points are in the right place. Let's try another one. All right, so this thing is not in standard form, right? For our standard form, we want x squared over a squared plus y squared over b squared equals the number 1. So in order to create that, I'm going to divide everything by 4. To at least create the 1, I need to do that, and then let's see what happens after that occurs. So I would have x squared, right? 4 over 4, that cancels, just leaving the x squared, plus y squared divided by 4, and then this would all equal 1 now. X squared is the same as having x squared over 1 squared. Y squared over 4, same as y squared over 2 squared. So in this case, a is 1 and b is 2. And this is the standard form of the ellipse. So from, again, the center is 0 because I don't have any shifts. If this thing were shifted, you would see additions or subtractions to x or y. Just like the circle, when it gets shifted, you have those additions or subtractions to the input. So we don't have any of those here, so this thing is just centered at 0, 0. And then from that center, I'm going to count 1 to the right and 1 to the left. Right, that's from this number here. Then from the center, 2 up and 2 down. So we get this little kind of vertically oriented ellipse in this case. All right, let's do one that's shifted. So here's the definition of our standard form when there's some shift present. So this is for an ellipse that's centered at HK, similar to our circle idea. We're taking the opposite of what we see here and the opposite of what we see there. So what I'll do first is find the center of this thing. It's already in standard form. So the center would be at -2. I'm taking the opposite of +2, and then the opposite of -3. So -2, 3 is the quote-unquote center of this ellipse. Based on the numbers, right, 9 same as 3 squared, so A would be 3. Not 9, but 3. 4 is the same as 2 squared, so that's telling me the vertical information since that is under the y term. So from -2, 3, so from the center, I'm going to count these distances now. So 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. All right, that's that. Let's try another one. I'm gonna type this into Desmos real quick just to make sure that it is indeed an ellipse. Don't forget that you can do this. You can type these into Desmos as a way of checking your work. Just give me a second on that. All right, it does look like an ellipse, okay. All right, so what we need to do is put this thing into standard form. So what we want to achieve is something that looks like x minus h all squared over a squared plus y minus k squared over b squared equals 1. So we want to achieve this. We want to transform this thing into this. Okay. So the first thing I'll do is I'll actually add over that 10. So we now have 4 times x plus 3 all squared plus 5 times y plus 1 all squared equals 100. And then again, I want to make this 1. So what I'll do is I'll divide by 100. So I'll divide by 100 each term. So 4 divided by 100, that's 1/25. So that'll leave a 25 on bottom. Plus, and then I have 5 over 100, that's 1/20. This all equals 1 now. To put this in standard form, I'm going to write a and b. Right, so I can write a squared and b squared. So this would be the same as x plus 3 all squared over 5 squared. So that'll tell me a is 5. Again, it's always under the x is a. It doesn't matter which one comes first. A is not the one that comes first necessarily, it's the one associated with x. Plus y plus 1 all squared over the square root of 20 squared. Right, this is the same as the number 20. And that's telling me that b is actually the square root of 20. This is all equal to 1. So we have a center of -3, right? Opposite of 3. Opposite of 1. So -3, -1 is our center. And then we have an a of 5 and a b of root 20. That'll be in between 4 and 5. So about 4.5. So just for our graphing purposes, b is about 4.5. We'll just call that good. Okay, so on to the plotting. So the center was -3, -1. Right there. Then from that center, I'm counting to the right 5 units. 1, 2, 3, 4, 5. Also to the left, 1, 2, 3, 4, 5. And then from that center, I'm counting up about 4.5. So this is not going to be perfect. 2, 3, 4. 1, 2, 3, 4. All right, there's our misshapen ellipse here. Okay, on to hyperbolas. There's this strange picture on page 181 of a cone. I think typically people think of like this thing as a cone, like those traffic cones, or you know, you're doing soccer drills and you're running through the cones. Usually it looks something like this. In reality, a cone is actually 2 of these. So this is actually a cone, technically. What we've been seeing, so section 11.1, 11.3, and now 11.4, these are all called conic sections. So if you're Googling around trying to look for this stuff, conic sections is a nice Googleable phrase. Why they call it conic sections is if you imagine slicing a section, like a cross section of this cone, if you do it this way, horizontally or parallel to the base of the cone, then you would get a circle, actually. If you cut it diagonally, but through the side of the cone, you'd actually get an ellipse. And now what we're seeing in this section is if you cut it vertically, what you would get are these hyperbolas. I know this picture isn't going to be great, but you'd actually get this type of shape, and that's what this picture is attempting to explain. Is if you cut it exactly vertically, then the plane that is formed is outlined by these hyperbola lines. So they're actually called conic sections because each of these shapes that we've seen in this chapter is derived from slicing a cone in some particular way. All right. So here are the standard versions of hyperbolas. So we have different orientations that are possible. So you could have a horizontally oriented hyperbola, and that's this picture where it's opening in the x direction, right? By the way, this is the hyperbola. This is the hyperbola. These are called asymptotes. We'll talk about those in a second. Or you could have a vertically opening hyperbola. Notice the difference. It's going to be hard to see here, but look here and here. When you have a horizontally opening hyperbola, it is the x term that is positive. Notice we have a minus now on these cases where the ellipse was plus, so that's the difference algebraically. So where the x term is the term that's positive, that will orient the hyperbola opening in this x direction. When you have a hyperbola with an equation such as this, notice the y is the positive and the x is actually the negative term. Now this is the positive, so this will be opening vertically. These asymptotes, so this is called an asymptote. So you may have heard of this phrase, kind of like one thing is asymptotically approaching another. So if something is asymptotically approaching another, that means as time goes on, that the two things are getting closer and closer together, but they're never actually touching, right? So that's what's happening here is these asymptotes kind of govern the long-term behavior of this hyperbola. So here is how we find the equations of those asymptotes. This b is the same b as you'd be seeing in your equation under the y. This a is the same a that you'd be seeing in your equation under the x. So you'll have a positive version, right? That'll give you this one. And then you'll have a negative version, and that'll give you this one. Let's try a few of these. All right. So for sure, this is a horizontally opening hyperbola. If the x is positive, then I'm expecting things like this. All right. So just to write it in its full glory, I'll write 5 squared minus y squared over 2 squared, just to identify what a and b are. This thing is centered at 0, 0, because there's no shift here. Just like we would see shifts before, we would see a shift here like that, but there isn't one. What that means, let me just summarize one other point. So once you know in what direction this thing is opening, we need to figure out how far to go. So that information comes from A, if it's opening horizontally, and it comes from B, if it's opening vertically. So this distance here would be a distance of B. This distance here would be a distance of A. So this one is opening horizontally because of the x being positive. So I'm now looking at this number, and that's going to inform how far I go to the right to make my vertex of that right side of the hyperbola. Then do the same thing to the left. That'll be the vertex of the left side of the hyperbola. But what I want to do before drawing the hyperbola is I want to figure out the asymptotes. Weird word, asymptotes. So the first one will come from, if you remember, it's b over a times x. The second one comes from negative b over a times x. A is always associated with x. So just to make that clear, a is 5 and b is 2. So y1, the first asymptote, would be 2/5 x. y2, the second asymptote, would be negative 2 over 5 x. So now you need to graph these lines. I'll do that in red. So I have from the center, I'm now using this slope to count up to and over 5. Right? So this, I wish I had a straight edge all of a sudden. That's okay. So this line will be that positively sloping asymptote. And then again, from this center, I use the other equation, and I'll go down 2 and over 5, and that will define the other asymptote. Okay, so that means that the hyperbola will tend towards those values in the extreme case. That's it. Let's try another one. So this is a case where it looks like the x is negative, the y is positive. This thing will be opening vertically, right? There's no shift. So it's still centered at this 0, 0. To write it in its full glory, I have y squared over 3 squared minus x squared over 4 squared equals 1. So in other words, b is 3, right? B is always under y. And a is 4, right? A is always under x, regardless of the location. It's not the location, it's the association, right? So these are associated always. All right, and then for the asymptotes, we'll have y1 equals b over a times x. And then we'll have y2 equals negative b over a times x. So in other words, y1 equals 3/4 x. y2 equals negative 3/4 x. So from this location, I'll count up 3 and over 4. So 1, 2, 3, 1, 2, 3, 4. And then from this location, I'll count down 3 and over 4. And then make your asymptote. I'm doing these in a dotted way, just to not confuse them with the actual graph. This thing is opening vertically, so that means I'm looking to B to know how far to go from the center. So I'm going to count 3 up and 3 down. And then these will kind of approach these asymptotes. All right. Moving on. So this one, I'll go ahead and do this one on page 183. It's actually a circle. I made a mistake, but we'll just get some circle practice here. It says graph the hyperbola. I believe it's actually a circle. So what I'll do is I'll get everything except the constant on one side. So I'm going to bring everything but this constant over this way. So I'd be able to write 3x squared, and then I'll subtract the 2x squared, right? And then I'll add the 9x, and then I'll subtract the 10y. I still have plus y squared minus x, and this would all equal 40 now. Combine like terms, get the x's near each other, get the y's near each other, all that good stuff. So I'll have just x squared, right, from those combining. Positive 9x minus x, so plus 8x. So maybe I'll just cross things off. And then I'll have a plus y squared minus 10y, and all this equals 40. Keeping in mind, I'm actually aiming for a circle. So the goal I have in mind is I want to convert this to something that looks like x minus h squared plus y minus k squared equals r squared. This was our circle. So it looks like I need to complete the square a couple times. So for the x's, b is 8. So half of b squared would be 8 over 2 squared. In other words, 4 squared, or 16. So I'll add that number in there, but of course also over here. For this part, I have b as negative 10. So half of b squared equals negative 10 over 2, and then I need to square. So negative 5 squared is positive 25. So I'll add that number there and also over here. So x squared plus 8x plus 16 plus y squared minus 10y plus 25 equals 40 plus 16 plus 25. So we should now have that this thing is a perfect square and this thing is a perfect square. And then we'll add all these up. We'll find our radius through those numbers. So it always factors as x plus half of b all squared. Half of b is 4 for this one. And then y plus half of b is negative 5. So y minus 5 actually squared equals 81. So I have that we have a circle centered at negative 4, 5 with radius 9, right? We always take the square root of whatever number is sitting here and we take the opposites as what we see here. So center negative 4, 5. And then a radius of 9. Not loving that, just because I have to count 9 now. So 1, 2, 3, 4, 5, 6, 7, 8, 9 maybe. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'd be making this fairly large circle. All right, going off the page with that one, but it's the work that matters. Just completing the square process is still around. Okay, I'll be doing the rest of the problems separate of the video. Please check in on the key, of course, if you want to see the answers to the other ones. All right, have a good one.